Hello, my name is Aditya Pillai, and this is Lab 4, Oscillations. The purpose of this lab was to use the energy and momentum principles to model the movement of an object oscillating on a spring. Some of the objectives for this lab include observing the change in energy due to force, comparing computational model predictions with observed data, and applying key physics concepts. Some of the concepts applied include the momentum principle, which can be derived to get the velocity update formula, the position update formula, and the gravitational and spring forces, as well as the energy principle, which in this case is set to 0 since the Earth is in the system. The concept of kinetic energy, gravitational potential energy, and spring potential energy are also applied. So this is the video that we analyzed in Tracker. We are given that the spring has a static equilibrium length of 0.7 meters, that the time between frames is 0.095 seconds, that the origin is the attachment point, and that the mass of the object is 0.402 kilograms. Some of the calculations we did include getting the period, which is calculated using similar points on the graph divided by the number of oscillations since then, in this case to get 1.5195 seconds. The spring constant, which can be found by rearranging the period equation and plugging the values to get 6.8736 newtons per meter. Calculating the net force equal to 0 equal to gravitational and spring force can give us the resting length of the spring at 0.127 meters. So this is the code that we used for Lab 4. Some of the changes we made in GlowScript include setting the mass of the ball, setting the initial position, the spring constant, relaxed length, and the equations to calculate the length, direction, and displacement of the string, as well as the kinetic energy, gravitational potential energy, spring potential, and overall energies. In the loop, we also calculate the gravitational force, spring force, and net force in order to set the velocity and position update formulas. We calculate the length, direction, and displacement of the spring, and then use those to find the energy changes during each iteration. So this is what the code looks like when it's run. The red dot is the actual position, and the blue is the model. The green line on the graph represents the change in spring potential energy, which is always directly opposite to the change in gravitational potential energy represented in red. The blue line, which oscillates twice as fast, is the change in kinetic energy, and the orange line, which stays at the center, is the change in overall energy. As you can see, the sum of the changes is 0. In the graph below it, of the recorded observations in red versus the modeled observations in blue, you can see that they are very similar with just a few discrepancies, which can be accounted for by human error in collecting the data. Overall, the model is accurate. After the lab, we were given two questions to answer. The first is, for the model system, is the energy principle satisfied? Justify your answer by discussing briefly the plots of energy changes. In this case, the energy principle was satisfied because it states that the change in total energy is the same as the energy applied to the system from the surroundings. Since we included the Earth and the spring in our surroundings, there was no outside input of energy, and as such, the change in energy would have been 0. This is a model of our prediction. In this case, the change in energy stays at 0, which is in accordance with the energy principle. The second question is, using the data you obtained in Tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. Compare the two estimates and discuss. The estimate from the y position, which we used in the GlowScript code, was 1.5195 seconds, and the newer calculated period for the x directional change was 1.52 seconds. They are very similar because the restorative force that causes the oscillation was the spring, whose spring constant was used in relation to the object's mass to find the period. At no point in the calculation were the x or y direction components used. As you can see in the equation, the only things used were the value of pi, the mass of the object, and the spring constant. In conclusion, there was possible human error in recording the data, as the real versus model graph was very close except for a few small discrepancies. The period in the x and y direction is very similar and ideally would be the same. The change in overall energy would be 0 because no work was done on the system. And the energy principle, combined with other key physics principles, is helpful in modeling situations including oscillating motion and non-constant forces.